Hi, I'm Andy Ingersoll, a member of the Cassini imaging team. Cassini has been in orbit around Saturn for 9 years, and we've been following this hexagon which surrounds the North Pole. It's bigger than 2 Earths, and it's a wandering jet stream. But it's been winter in the north, so we have not been able to see what's at the center of the hexagon. But now it's spring. And what we found at the center of the hexagon is a Saturn hurricane. This is a view from directly over the North Pole, which is made possible by the orbit of the spacecraft, which is now taking us over the poles. The winds are flowing at 300 miles an hour, which is 4 times hurricane force. The fluffy white clouds in the center are about the size of Texas. We can use special filters to measure the heights of the clouds, and the red are low clouds and the green are high clouds. We call it a Saturn hurricane because it has the eye, it has the high winds, but it's different from an Earth hurricane because it's locked to the North Pole. And unlike a terrestrial hurricane, there's no ocean underneath. And that's one of the puzzles we're trying to figure out.
My name is Bridget Hessman, and I'm a planetary scientist at NASA's Goddard Space Flight Center, and I study storms on Saturn. A great white spot is a massive storm system that erupts on Saturn about once every Saturn year. The great white spot that erupted in December 2010 first presented itself as this fluffy white storm cloud that popped up in the northern hemisphere. The storm, when it erupted, sent large waves up into the stratosphere, and we saw effects like an increased amount of ethylene, something we never expected to see. In the coming days, the winds on Saturn sheared the storm in both directions, and it wrapped all the way across the planet. If you were to scale that to a storm system here on the Earth, what you would have is a storm system that covers all of North America but wraps around the entire planet. There'd be no escaping this storm system, and it would be lasting for a very long time. This great white spot happened to occur 10 years before we expected it, which was very fortunate because we happen to have a spacecraft called Cassini in orbit around Saturn. And that spacecraft has a full suite of instrumentation that allows us to study this over all wavelength ranges. Some of the effects that we got to see in the infrared were these 2 bright beacons that started to shine right after the storm erupted in December. Those beacons at first showed temperature differences of about 20 Kelvin, which is reasonable for a storm. However, as time progressed, we started to see even larger temperature changes. By May 2011, the 2 beacons had merged into one, and we saw a temperature change of over 80 Kelvin from the quiet conditions before the storm. So that would be like going from the depths of winter in Fairbanks, Alaska, to the height of summer in the Mojave Desert, all in one storm system. Can you imagine what that would feel like sitting on your deck? We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit allowing us to make a historical record of this great white spot.
We don't really know on Earth why you get thunderstorms at the rate we get them. We look at Saturn, they're very infrequent.
We were pretty sure that lightning exists there, but we actually couldn't see it. It's a giant planet with huge atmosphere, and there should be a lot of weather there.
We had heard the lightning on the radio instrument on Cassini, but you hear static on the radio signal, but you can't pinpoint where it's coming from. We had to use a synthetic noise because the actual noise that the radio instrument is picking up is beyond the human ear. So we picked a noise that sounded like an electrical discharge. In other words, a big spark. That's what lightning is. It's taken us a long time to see the lightning, and that's because normally the night side of Saturn is very bright because the rings are shining down all the time. The night side of Saturn is brighter than Earth under a full moon.
The strategy we chose was to look at the equinox. And the equinox is when the sun is in the ring plane, so it doesn't illuminate the rings that much. And rings become dark, and this night becomes dark.
When it finally got dark enough at night, we pointed the cameras there, and wonder of wonders, there were lightning flashes, and took a series of pictures. And in one picture there'd be no lightning flash, and the next picture there'd be a lightning flash. And at the same time, you hear the noise over the radio instrument.
And we actually saw it. I didn't believe it.
The lightning storms on Saturn are very much like lightning on Earth. You get the same strength lightning storms, or thunderstorms. They have the same strength, but they're just much less frequent. I'm enjoying the show.
The solar system's giant planets might also produce tornadoes. Jupiter, Saturn, and Neptune are already known for their swirling clouds and hurricane-like storms. On Saturn, the Cassini spacecraft captured a photo of the planet's southern polar region, showing some twisted clouds that look familiar. They are intriguingly similar to the Doppler radar hook echoes that are said to be signatures of tornadoes inside supercell thunderstorms on Earth.
I wouldn't be a bit surprised if one day we can nail it and say that this is in fact a tornado on Saturn. But right now, our instruments are not fine enough to make that conclusive judgment.
In February 2005, we had our first close flyby of Enceladus, and the magnetometer signal saw something unusual.
What a magnetometer does is it measures the magnetic field in the vicinity of the instrument. We had a look at the wiggles, and they looked strange. The magnetic field of Saturn is moving towards it, and it couldn't penetrate down onto the surface, which was pointing to an atmospheric signature of some kind.
Here it looked like it had a tiny atmosphere. In March, we came even closer, looking for that same strange signal.
What it showed was that the signature, the atmospheric signature we were seeing, was focused at the South Pole. It was almost like there was a cometary plume of water vapor coming off from the South Pole.
People were saying, it's gotta be jets, it's gotta be jets, and the imaging team was saying, no, we don't want to say that, until we're sure. And so we went closer. We came within 175 kilometers of Enceladus.
Then we got the data back, and it was spectacular.
And then we found the evidence. Geysers coming out of the South Pole with water vapor and water ice particles. They were active geysers at the South Pole of Enceladus.
Because we were so close, all of the other instruments were able to take really good data. And we put together all of this data. We saw the cracks, the tiger stripes of the South Pole. We saw heat leaking out from these tiger stripes. On subsequent flybys, we found organic material, dust, water vapor coming out of the plume.
The Cassini discoveries in the first 3 flybys were so amazing. We changed our focus and added 20 more flybys of Enceladus, including 7 through the icy jets. The surprising magnetometer reading led us to the liquid water ocean underneath Enceladus's icy crust. After over a decade of research with Cassini, we now know there's a potential for the ocean on Enceladus to support life. And that has altered the way we think about where life might be found in our own solar system and in the worlds beyond.